So I want to be clear. We're going to move things back one day. So, because on your schedule, if you have your schedule, it says we're supposed to have the practice exam day after tomorrow, Thursday. Let's move it back. I looked ahead at 5.3, 5.4. They're pretty meaty sections. So let me be clear. I'll write it right here. It'll be on the recording as well. So basically, next Tuesday. What is that date? The 2nd? No, 3rd. 3rd, Tuesday, October 3rd. Next Tuesday will be the practice exam. That was going to be the exam. It's set on the schedule. That'll be practice exam number 2. You know, we'll do the same thing. First hour, take it. Second hour, I'll go over it. And then next Thursday, October 5th, will be the actual exam number 2. We're going to push things back one meeting because I want to spend more time on 5.3 and 5.4. They're really pretty big sections. Make sense? Is that good? So exam's next Thursday, in other words. Practice exam next Tuesday. Next week's test week. All right, so let's move ahead then. So we've got some big sections. So I'm going to spend really all this week just on 5.3. I think they're worth 4 hours, 2 hours today, 2 hours Thursday. 5.3, 5.4 are that big, especially 5.4. All right, so they're giving us exponential functions. What 5.3 and 5.4 are all about is exponential and logarithmic functions. What are they? First off, an exponential function is one where the x climbs into the power zone, exponents powers. But it's not just that it has powers, but that x itself has climbed into the power zone. So it'd be something like 2 to the x. That's exponential. It's exponential. And you could have other things in there than just that. Like you might have 3 times 2 to the x plus 5 or whatever. Whatever. As long as x is in power. So x in the power zone. That's what makes a function exponential. In other words, something like x squared is not exponential, even though it has powers. Excuse me, my voice is a little funny. So it's not just that it has powers, but that x itself is in the power zone. That makes it exponential. That'll be a big deal if you're going into calculus, because the way you do the derivative is completely something you do all the time in calculus, called the derivative, is totally different for a function like x squared, which is really just a polynomial. What would you call it? You just say that's a polynomial, Just, the x squared plus 3x, x to the 7th plus x squared plus 3x, whatever. That's just a big old polynomial. It's not exponential, and it means a certain thing about how you do the derivative in calculus. Whereas something like this, where x has climbed into the power zone, that's a big deal. And what it is, it's a more powerful function. It goes up super, super fast. Their graphs rocket up, which we'll look at in just a minute. So anyway, first off, let me give you the definition, what we're talking about today and Thursday. Exponential functions, and then on Thursday, logarithmic functions, which are actually just the inverse of exponential. That's what they are. Okay, so what about it then? Well, we're gonna talk all about it. We're gonna start with tables. Then we're going to move to graphs. Then we're going to move to equations. We're going to look at exponential functions, like when you make tables, when you make pictures, and when you deal with the actual x's and moving them around and stuff. So that's the plan. Then we'll do those same 3 things for logarithms in the next section, big meaty sections. Okay, so first thing is they say, hey, can you just look at a table of numbers, and just simply from the table, could you decide if the thing is linear, exponential, or, and the word's off the screen, but it should be neither. It's either exponential, logarithmic, no, let's try that again, linear, exponential, or neither. How do you know? Well, it's all about what's happening with these y, but f of x is y, right? It's all about what's happening from y value to y value, meaning if you're adding the same number every time, it's linear. Let me write that. Linear, if you add or subtract. When I say add, I really always mean add or subtract, because if you add a negative, it's subtraction. Add, subtract, same number. If you add, subtract the same number every time, then that's linear. It's exponential if you what? Multiply or divide. Yeah. See, it's a level up. If you multiply or divide, same number every time. You ever think that way about the operations? What was the first math operation you learned when you were a kid? It was adding, right? That was when math was easy, huh? Weren't those the days? Just adding, subtracting. Then you got a little older, and you did multiplying. I still remember me, your math teacher, being scared to death to have to do my times tables before Miss Unmack in the 4th grade. We all had to go to the front. I don't know if they put that kind of pressure on kids anymore. Anyway, you had to go to the front. I mean, not in front of the whole class, but you just had to go up to her desk and say all your times tables, and I was scared to death about all that. So things were harder multiplying, and then dividing. Well, the math operations, that's a true way to think about them. They're like, it's like adding, subtracting are like the bottom level, and then multiplying and dividing are one notch up. What do I mean a notch up? Well, multiplying is repeated adding, isn't it? What is 3 times 7? But 7 added 3 times, huh? Multiplying is repeated adding, so it's a level up. Dividing is repeated subtraction. I don't know if you think about them that way. They both make things smaller, but dividing is a higher level. What do I mean? Well, how many times does 2 go into 6? Well, 3 times. What does that mean? You could subtract 2 repeatedly 3 times. That's what that means. Dividing indicates repeated subtraction, and multiplying indicates repeated adding. So they're a level up. Multiplying and dividing are repeating, instantaneous repeating of the lower level operations. And then one level higher than that is powers, like 2 to the third. What does that mean? Repeated multiplication. See how the hierarchy of operations goes? That's where the PEMDAS thing, I'm getting way too far afield. I'm explaining all of math and how it all fit. We don't have time for that. But anyway, that's generally where the whole, the PEMDAS, please use Madeira and Sally, right? Multiplying, dividing, adding, subtracting. Exponents are up here, right? That's what's going on. It's kind of helpful. It isn't totally far afield. It is helpful to, that's what's going to be going on, especially with the log rules on Thursday. They basically they're dialing in to this hierarchy. That's what they're doing. So you want to think about exponential with x in the power zone as a higher level kind of operation, and that'll have to do with how all these equations and formulas work out. If you kind of keep that in the back of your mind, it'll help you remember why the equations are doing what they're doing. All right. So with all that said, adding, subtracting is simply linear, and multiplying, dividing is exponential. It's a level up. So. And then if it does neither, it's neither. So what's happening? From 3 to 5, you add 2. Is that what you do on the next one? No, then they're adding 5. So this one's neither. This one's neither adding the same number every time, nor is it multiplying the same number every time. This is neither. Let's get to the next one where it'll do something. Okay, so number 2. How about that table? Let's look at that one for a second. Let's ignore the fraction. I'll come back to him. Let's just start at the 1. What do you got to do to 1 to get 3? Well, you could add 2, but that wouldn't work for the next stop. You'd have to add 6. It's not adding, is it? What is it?
Multiplying.
Yeah, you can clearly see it's timesing by 3, isn't it? Times 3, times 3, times 3. Right? The y values are multiplying by 3. Does that work even for the 1/3? Yeah, 1/3 times 3 is 1, huh? All right, so it's multiplying by 3 every time. So what kind of function? That table is indicating what kind of function? Exponential, right? It's multiplying by 3 each time, so it's exponential, right? If it was adding or subtracting the same number every time, it'd be linear. All right, so it's exponential. Okay, so what? Well, now, because they want more than that, they want you to say, okay, it's exponential, but now they want the equation for it here. How do you look at the table and come up with the equation? Well, let me give you the basic look of the thing. The basic look of the thing is a times b to the x. Now, it can also have a plus c in there, but they're not going to do that for the table ones, so I'll just leave it off. But in a minute, when we go to the pictures and the graphs, I want you to know I will put a plus c in there. That can be part of the deal. They're just not going to push us quite that hard on the tables. So a times b to the x. So we're looking for the a, and we're looking for the b. Once we find those, we have the equation. You guys come, that reminds me to stop right there for just a second and say, do you know what it means when, in any math problem, when they say find the equation? Sometimes the lingo in math can be part of the battle. Whenever they say the words find an equation, you know, right, that what they want is a y, x thing, and then some numbers. I just want to be really clear on that, right? In other words, x is going to say x and y is going to say y. I'm not going to do anything with them. But they mean find A, find B, and you'll have the equation. That's what it means, right? An equation still has x and y, and then numbers, right? All right. So they're asking me to find the equation, which really means here's the general form, which you'll want to put on your 3x5 card for next week's test, and find A and B. How do you do it? A is the y value next to x equals 0 in the table, meaning 1. So the A is 1 for this problem, right? So I go to the table, go to x equals 0, and grab the y value next to x equals 0. That will be your A. I'll give a reason for that in a minute, but for now let me just say it. It's the number next to x equals 0. It's the y value in the table, across from x equals 0. All right, and what's the B? Does anybody know already? The B is the number you're multiplying. Yeah, it's the 3. B is that 3. So 1 times 3 to the x, there's our equation, or formula. We're done. And you don't need the 1, huh? 1's not doing anything. You can just write 3 to the x, and that'll be fine too. We got it. Now hold on. Is that true? What we're saying, let me show you that is true. Let's go over to the table real quick. We're saying that this y values are really coming from 3 to the x. Is that true? Let's plug in, let's start here with -1. If you plug in -1, what is 3 to the -1 power? Do y'all remember from your algebra days what negative powers do?
Fractions.
Yeah, they flip it and make it a fraction. Do you remember that? That'll be an important thing to remember in this section and the next. In other words, it's not -1/3, is it? It's a positive 1/3. So negative powers don't put negatives in the front, they flip things. Remember that? So yeah, that's right. 3 to the -1, it's working. How about the next one? 3 to the plus 2 is 0. What am I doing? 3 to the 0. I'm just doing them one step at a time here. So y equals 3 to the, plugging in the x, 0. What's anything to the 0 power? Remember, it's 1. Anything to the 0 power is 1. Now let's try the next one. 3 to the 1 power, 3. See, it's working, isn't it? 3 to the 2nd power, 9, etc. It's working. That is indeed the formula cranking out those table values. All right. I will move on. 3. All right, try that one. Let me give you a second now that you know stuff. Skip the fraction if it bugs you and just start on the second line. I'm trying to find out, is it adding the same number every time, multiplying the same number every time? What does it do? All right, what's the story? I'll just start at 7. 7 times 6. Use your calculator. It is times 6, huh? Check in your calculator. It's multiplying by 6 every time, isn't it? And you can tell the first one, yeah, times 6, it'll cancel that 6, it'll be 7. Yeah, that's right. So it's multiplying by 6. So it's exponential. Again, exponential. And so it's y equals a times b to the x. The b is the 6. It's the number you're multiplying by every time. What's the a? Yeah, the a is the number next to x equals 0. It's the 7. So this is 7 times 6 to the x. There we go. Is that good? Making sense? Hey, do you see now why the a is just the number across from x equals 0? See how that works? Right? If you come down here, you can see when you plug in the 0, y equals 7 times 6 to the 0. The 6 to the 0 is just 1, and so you just get that number in the front, huh? That's why across from 0, when you plug in the 0 to the x, right? 7 times 6 to the x. When you plug in the 0 for the x, this part's just going to go away, or become 1, I mean. So y will just equal the number in the front. That's why the number in the front always comes from what's next to x equals 0. Is that good? Is that making sense? Questions I can answer on that? All right. How you doing? You guys are giving me the straight face. I'm trying to read you. Is it good? Is it bad? Okay, try that one. Same kind of thing. Look at those y values. This will be our last table. We'll go to graphs next. So what's happening from y value to y value? It's adding 4 every time, isn't it? So that's what? Linear. Now, I haven't given you the linear setup, but you kind of know it. It's mx plus b. So we know it's linear, so you know linear, y equals mx plus b kind of thing, right? Now, what's the m? The m is the slope. And what's the slope? It's actually that number added each time. It's the 4. Do you realize that when you add the same number every time to the y value, that is a slope? Because you see x is going up by 1 every time. So this is rise over run, do you realize? So the slope is just 4. that number being added every time is the right. If you graphed it, how about this? Maybe it'd help if I graphed it. What does this mean? This means that 0, 6 over 0, up 6. 1, 2, 3, 4, 5, 6. 0, 6. The next point, 1, 10. Over 1. Well, I'm getting out of space here. Over 1, up 10. It would be up here. What did it do? Went up 1 over 4. You see that? No, that's backwards. Up 4 over 1. Went up 4 over 1, didn't it? So that's just a slope. That number being added every time is just a slope. It's the rise in y values. It's the rise. And the run is just 1. We're giving a table where the run only goes up by 1 every time. So therefore, whatever the rise is on the y values, that is the slope. Because rise over run, the run's just 1, then the rise is the rise over run. It's the slope, isn't it? So the added number is 4. And what's the b? Yeah, it's 6. It's the number across from 0 again, just like in for the exponential. Because it's the number when you plug in 0 for x that y will equal, huh? Works the same way. Yep, so there we go. So they want you to choose linear, whoops, right down here, linear, and write 4x plus 6. There we go. So we good with that? We're going to leave the table stuff. You okay with that? Find a linear, exponential, and so just put those on your 3x5 card. Those little setups. And off. Now we want to talk about exponential graphs and what they look like. So let me give you. Let's do this the way we've done all the graphing in the class so far, which is, I think, a very helpful way. I hope you're feeling more and more strong at graphing. Give you the basic one, and then we'll do the twists and the turns and the flips like you already know how to do. So let me just give you the most basic general. Y equals a times b to the x plus c. So just generally, what does an exponential graph look like? Well, in general, they have, first thing you need to know is they always have a horizontal asymptote line, and it's at C. That's the horizontal asymptote line. So you go up to C, at C, and you put a dotted horizontal asymptote line. So exponential graphs have a flat horizontal asymptote line. Okay, next, the A. What the A part of the puzzle is, graphically, it's how far above the things messing me up, horizontal asymptote to the center point. In other words, this right here, this dot, this distance from there to there is A. It's usually 1. It's almost always just 1. Yeah, let me draw that a little bit better here. Let me make it bigger. So let's put it right here. So from there to there, that distance is A. Does that make sense? So the horizontal asymptote's at C. The jump from there up to the center dot is A, whatever that number in the front is. Okay, put all this in your 3x5 card. And then the B doesn't matter a lot, even though you'd think it would. It seems kind of central. Just generally from there, you know, the graph just rockets up like that. Now, of course, we're looking at one that goes down. We'll talk about why that one's different. But the general one rockets up to the right. Exponential growth is really, really fast growth. You'll hear them talk about that in the news and different things. They'll say such and such is growing exponentially, which means super, super fast. Like, just think about 2 to the x for a minute, for example. If you were to make a table of like 2 to the x and just plug in 1, you'd get 2 to the 1, which is just 2. That's no big deal. 2, 2 squared, 4, 3, 2 cubed, 8, 4, 2 to the 4th, 16. It just keeps doubling, doesn't it? Notice how it'll 5, 6, 7, 8. By the time you get to 10, it's at 1,024. Do you know that? If you just did 2 to the x, by the time you're over here at 10, that thing is up at 1,000. It's past 1,000. So it's rocketing up way faster than like an x squared. I know we think of x squared, the U shape is going up fast. This thing will make x squared look like a snail. It'll go up way, way faster. Getting x up in the power zone is way more powerful than just having a power. That's weak. This is weak compared to exponential functions. They're a whole level above, like, yeah, the hierarchy thing. They're a level above. Their growth is a whole level above. All right, anyway, so in general, they rocket up to the right. That's what they generally do, unless you what? Flip them or twist them or do something like that. So what I'm giving you then is the general, just like we memorized those basic 6, absolute values of v and x squared is a u shape and those basic 6, and then we learn to flip them and twist them and move them and stuff. Same thing here. I'm giving you the general, and then on Thursday, here's the general exponential. On Thursday, I'll give you the general look of a log, but then we'll twist them and flip them and stuff. So here's the general look of an exponential. Now, looking at this one then, what do you think has been, well, first off, let's try to piece this one together. Looking at this one, it's always good to start with the horizontal asymptote, which is the number added or subtracted off to the right. Right? The A is multiplied, notice, and the C is added, subtracted. So the horizontal asymptote is whatever's added. So what's the horizontal asymptote? Well, y equals 0. So that's, clearly what's being done here. It's y equals a times b to the x plus 0. Right, this y equals 0 is your C. Good so far? Kind of going from the graph to the equation now. So, okay, what's the A? Can you tell what the A is? What's the A again? It's how far above. Its A is right here. It's this gap from the horizontal to the center dot. Can you tell in this picture? It's kind of hard to tell. 1, 2, 3, 4, 5, 6, 7. That looks like 7 to me. Right here, this dot is up at 7. This gap from there, let me get this other thing out of the way here. This gap from here, from the horizontal up to the center dot, looks like 7. So that's my A. You with me so far? So I got my A, my 7. Don't even look over there yet, because they're going to do a trick over there, and I'll explain that in a minute. Yeah?
If it's going the other way, the graph, would it be negative 7?
Good question. Let's talk about that. Yeah, so now we're ready for that exact question. It's right where we're at. So, good so far, right? We got the jump up here, 7. Got the 0 horizontal asymptote. Now what about the fact that the graph, instead of like the normal one rocketing up to the right, it's dropping down to the right? What makes that happen? What just aside from equation stuff for a minute, just visually, what do you do to this graph to make it become that graph? What do I do? Do I flip it vertically? Do I flip it sideways? Which one? Flip sideways. Does everybody see it's a grabbing of this rotisserie and turning it right there? It's been flipped sideways, actually. Now, if you flipped it vertical, that'd be down like this. We'll have some of those in a minute. That would be a vertical flip. That's not what's been done, huh? It's been flipped sideways. Somebody grabbed this y-axis and rotated it, and the graph went, oh, okay, I'll go over here. Woo, like that. That's what he did, huh? Does that make sense? So they flipped it sideways, didn't they? So that's an X flip. It's an X flip. You agree? Sideways, X flip. So now the question is, what makes an X flip in an equation? Now we're ready to talk about equations. What does that? To any equation, not just this one. Any equation, what have we learned makes an X flip happen? You put negative on the X. Right there, huh? Not negative in the front. If you put negative in the front, what would that do? That would be that goes down. That'd be the vertical flip. And we'll do some of those in a minute. Everybody good with those two? Remember what we learned about y effectors, x effectors? Right? So negative on the y would make it jump down. Negative on the x is a sideways flip. That's what's been done. So this is a negative x. And by the way, look at all the bases are 7. So the base is clearly 7. So you can just tell from the multiple choice options. So therefore, what do we have? 7 times 7 to the minus x plus 0. That must be the equation. But I don't see it there. We'll talk that out in a minute. But everybody good so far? That good? This first 7 is because of that gap of 7. This other 7 is because they're all base 7, right? Notice all of the bases are 7. When I say base, I mean the number that has something on it. That's what a base is, right? It has something on it. So they're all base 7. So you need the 7 in the front for the A. You need the 7 for the B because they're all base 7. You got to have something as the base. Negative x for the sideways flip, 0 for the horizontal asymptote. Now, let's go through and do process of elimination because I don't see it. They're making it look different is the trick. So let's go through and just eliminate. We got to have negative x in the power zone. So bye-bye, 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 right? All those had positive x in the power zone. They're wrong. We got to have negative x in the power zone. So we're down to 3. down to 3. Not this one. That has negative in the front. We gotta have negative. There's no negative in the front here. That would make it flip down. That's not right. So I got rid of D. We're down to 2. It's B or it's G. You guys like me to give 8 options for the multiple choice? No, it's not. We'll stick with 5. Okay, so B and G. So which one is it? Well, do you see the trick? There's another way. You got to remember an exponent rule. Remember the rule. I bet you do if exponent. Remember like 2 to the 3rd times 2 to the 4th or whatever. Remember what that equals? 2 to the 7th. You add the powers, right? You add the same base multiplied, add powers, right? Well, this has really 7 to the 1 here, right? Same bases multiplied. What do? 1 plus negative x. And plus a 0 out there. Which is the same thing as 1 minus x. There it is. See that? They just did it in a tricky form. That's the same thing, huh? So there we go. We good? Everybody see that little trick, right? Same bases multiplied. You can put it like put these two 2's together in 1, 2, add the powers, right? So I put these together, 1, 7, 1 plus negative x, which is the same thing as 1 minus x. There it is. All right. I thought you'd be really happy about that. So I'm looking for happiness. I'm aiming for... All right. All right, try that one. The base is clearly 4, huh? They all have 4 as their base, so you can just throw that in for B. So write the general form. You know, it's y equals a times b to the x plus c. You know the base is 4 because they've all got a 4. So just throw that in right away. So you just got to find the a and the c now. And maybe there's negatives in different places. See what you can do. What's the c? C is always the horizontal asymptote, which is just the 0, huh? The dotted line, sideways dotted line, so that's just 0. Fill that in as a 0, or you can just skip it, 0. What's the A? Remember, A is the jump from the horizontal to the center dot. So right here, it's how far from the horizontal to the center dot. That's always A. So notice it's down 1. It's negative 1. Negative 1 times 4 to the x. Plus 0, we will skip that. Does that make sense? And in fact, that negative in the front is what's making the graph, because normally they go up, huh? The normal one goes up, 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 and away to the right. This one's clearly been flipped downward. But not just downward. What's been done then? Then they've turned it sideways as well. Meaning they put negative on x. Am I going too quick? I was going to let you do that one on your own, but I just got interested in it. I should have given you another minute to work on it.
I'm going to do the next one.
So that makes sense. Let me go through it a little slower. So 2 things have been done to get this result. Yeah, I should have let you do that one a little bit better on your own for a second. So the normal one goes up like that. This negative here, this is a y flip, right? That flipped it, well, I'm not drawing that very well. That flips it downward. But then this is an x flip, which flipped it sideways so that it ends up as it really is. So they flipped it down and they flipped it sideways, so it goes like that. Right? Both flips have been done on that one. So that's what we're looking for. Where's that one? Is it? It's D, right? No, yeah, it's D. So there it is. Is that okay? Let me let you digest. I went too quick. I'll let you digest that for a minute. See how it's 2 flips there? Vertical and sideways. And the A, remember that A is the gap from the horizontal to the dot. If it's down, then the A is negative, which is also explaining the vertical flip, both. All right. I'll keep. All right, try that one. How we doing? Making sense out of this. So all the bases are clearly 5, so it's a times 5 to the x plus c, right? The bases are all 5, so, okay. Now, the normal, what's the a? The a is the jump from the horizontal to the dot. Looks like it's down 1 again, huh? So the a is negative 1, and the c is 0 again. So, and now, this graph, the normal graph goes up to the right. This graph has been flipped vertically, y flip. But that's it. It's not been flipped sideways. It's just been flipped down, and that explains everything, doesn't it? So it must be like that. So it's this one, right? We good with that? Making sense? Questions? Put that on your 3x5 card and make that happen. They're going to push us a little harder now. Okay, try that one. Let's write the general setup again. A times b to the x plus c. Y'all getting that one? All right, so the asymptote this time is negative 1. So that's the C, the horizontal. The bases are all 4. So I'll fill in the base, fill in the C. Good so far? Right, the horizontal is negative 1. That's your C. Right, the C is always the horizontal. And the B is 4. They're all 4. What's the A? What's the jump from the horizontal to the center dot? It's just up 1, isn't it? The jump is positive 1, looks like, isn't it? Everybody good? Right, from the horizontal to the center dot is positive 1. So it's like that. Has the graph been flipped? Or no, he's doing the normal. He's up to the right, like the normal. He's not been flipped or anything. So that's it, right? So just 4 to the x minus 1, just e. Is that good? You can always make tables too, by the way. In the middle of the test, you're like, I'm not sure about something. You could always do the table thing. It just takes too much time to be like doing that all the time, probably. But if there's like one question left, you know, and you're not sure and you really want to get it right, just you could plug, you say, well, I don't know, so let me try a couple values. 4 to the 0 minus 1, that'd be 1 minus 1, 0. Does it go through 0, 0? Yeah, it does. It goes through 0, 0. That's looking good. Put in a 1. 4 to the 1 minus 1, that'd be 4 minus 1, that'd be 3. Is it over 1 up 3? Does that look right? Oh, yeah, look at that. Over 1 up 3, yeah. That's it. That's working. Yeah?
Is there a way to find the base?
And, what do you mean by, like, you mean that dotted line, or?
Oh, the B?
Oh, yeah, no, yeah, you don't have to, though, because they're going to, same thing on the real test, I'll just give you multiple choice, and it'll be all the same base. But yes, technically to answer, you know, for full math knowledge, you'd have to find actual dots. In other words, say they just gave me this graph, and they didn't give me any multiple choice, you know, and I wanted to find the base. I'm not going to require that of you. But here's what you could do. You could go, look, it's y equals, you know, you'd know the a in the front's a 1, and the c is a negative 1. So I'd go, okay, it's 1 times some base to the x minus 1. I would know that much just from the graph, even if I had no multiple choice options, right? Then how would I find the b? I would make a table. And I'd come over here, and I'd say, well, look, looking at that, I know, looking at the graph here, I know this is the point over 1 up, 3. So I would try it out. I would put in a 1 for x and a 3 for y, like that, and then I would solve for b, you see. That's how you would do it. Add the 1 to both sides. You would get 4 equals 1 times b to the 1. In other words, 4 equals b. You go, the base is 4. But I won't require that much, but it's a good question. That's how you do that. All right. There's always more. I'm holding back mercifully. Too much math requirement, you see. Let's look at another one here real quick. All right. So y equals 4 to the x plus 2. So which of those graphs is 4 to the x plus 2? Well, I've checked the b already there for you. I don't know if you notice a little green check mark. Do you see that? It's b. Right, because the 2 is the horizontal. So you put a horizontal at 2, right? Oops, that not very, that one doesn't look very flat. So 1, 2. So that one's at 2, horizontal at 2. Right? What's the a? I don't see an a in front of this thing. So it must be 1, huh? You with me on that? Everybody see there must be an understood 1 there in the front because there's nothing showing. So the a is 1, which is what? The jump. The jump from, so in other words, the dot must be right there at 3. Am I going too quick? You tracking with me? The horizontal's at 2, plus 2, up 2. Right? This is 1, 2, 3. So the horizontal's at 2. And then the a, what number is in front? There's no number in front. That must be 1. It's a jump of 1 from the horizontal up to the center dot. That must be a 3. Okay? And then this is just 4 to the x, meaning it's not a negative ag. There's no negatives anywhere. So there's been no flips of any kind. So it just does the normal up to the right. And I maybe I should have been saying, it comes down for a landing on the horizontal asymptote the other side. It doesn't ever touch it, but it gets closer and closer. You know, you're aware of that, right? It gets closer and closer and closer to that forever is what it does on the other side. And then it rockets up on the right. So yeah, so that's B. Good. On that. Yeah, it's real easy. They also want domain, range, horizontal asymptote. Okay, so what's the domain of this thing? What's domain? Yeah, domain, remember, is width. On a graph, when you have a picture, domain is cake. Domain is just left edge, comma right edge, isn't it? With parentheses. So it's negative infinity, regular infinity, isn't it? Domain, that graph goes forever left, forever right. Forever left, forever right. And what's the range? Well, bottom, top. Remember, range is bottom, top. It's the vertical span. So what's the bottom? What's as low as that graph goes? 2. And it doesn't touch the 2, parenthesis. It's closer to the height of 2 forever. This is the bottom. The top is infinity, isn't it? 2 to infinity for the range. And then they ask, what's the horizontal asymptote? Well, we found that it's this. It's this dotted line which goes through the y-axis at a height of 2. So y equals 2 is the horizontal. Those are the other 3 questions they ask. So I'll move on. They're going to push us a little bit on our power rules. So they're going to go y equals 4 times a half to the x. Now, I didn't give you one like that. I mean, I didn't give you like a rule for fractional bases. Here's what you should do. You should recall that 2, what's 2 to the minus 1 power? What does the negative power do? Flip. So 2 to the negative 1 power is a half. Do you realize that? Right, because it's 1 over 2 to the 1, or just a half. Right, because negative powers flip, right? Let me make that more clear. What would 2 to the negative 3 be? Let's review that for just a second from your algebra days. Well, first you flip it, and then you do the power thing, be 1/8. Is that good? So negative powers, do not put negatives in the front, right? This answer is positive in the end, isn't it? They don't put negatives in the front. They flip, and then you do the power thing. So 2 to the negative 3, flip it, and then 2 to the third, 2 times 2 times 2, 8. Good. So then 2 to the negative 1 is just 1/2, isn't it? So what? Well, that means this is 2 to the negative 1 to the x. In other words, and remember, powers multiply powers. Powers, I should say, powers outside parentheses multiply powers inside. So in other words, this is 4 times 2 to the minus x. That's really what they're saying. When they put that half there, that's 2 to the negative power. That's what that is. So that's a graph that's been flipped sideways. That's what that half ends up doing, because it's 2 to the negative power. It flips that graph sideways because it's really a negative power. That's what a fraction really is. So now we're making some deeper level connections between fractions and powers and negatives and graphs and flips. These are the things you've got to grab hold of for calculus. So is that making sense then? So you make those little changes and you go, oh, okay, so I'm looking at this. I know how to graph that. That just means, what's the horizontal? Let's put the horizontal on there. Horizontal. All together. 0, right? There's nothing out there. Just 0. So the horizontal 0. The horizontal asymptote is just 0. It's just the number added to the right. So there's nothing. It's just 0. And then the 4, what does the 4 do? That's the jump, right? That's the jump from the horizontal up 4. 1, 2, 3, 4. Boom. Right there, 4 is the center point. And then normally it would go up to the right, normally. But what does the negative x do? Turns it sideways, right? So it's going to go like this. So this is the actual graph. Like that. Is that good? So which one is that? Is that D? It looks like D, doesn't it? Yeah, because, D is the only one that's up high going down to the right. Is that okay? Did I do that too quick? You good? So when you see the fractional power, like a half, you got to write that as a negative power, because that's what fractions are, is negative powers. They're going to push that a lot in this section in Thursday, logs. And with logs, you'll have to do it backwards, because logs are inverse exponential. You really got to be clear on that truth to be able to handle it backwards. Fractions are negative powers. Fractions are negative powers. Okay, I can try that one. 5 to the x plus 2 minus 2. Okay, so what's this minus 2 out here do? That's our horizontal asymptote. 1, 2. Right down here, minus 2, good. What's the A? What's the multiplied number in the front? There's nothing in the front. Must be a 1. Good, that's my A. That's my jump. Now what is that? That's the jump. Remember, A is the jump from the horizontal to the center point. So it's a jump of 1. So it must be there at negative 1. So the A is positive 1, jump from the horizontal up to the dot. Everybody getting the hang of what that A does? Is that making sense? Okay. Now, the normal graph, normally the graph goes through that dot and up to the right, normally. You know, if they just gave me x, but they gave me x plus 2. No negatives. No negatives. There's not negative x. There's not a negative multiplier. So I'm not flipping anything. No flips here. But x add 2. Now you know what that does to a graph, huh? What does adding 2 to x do to any graph? left 2. Remember, x does the opposite? And anything you do with x is right, left. And it's opposite, so it's going to be left 2. So now, that means you move the entire graph left 2. Now, the easiest way to do that is grab it by that center point. That's kind of like a handle. Go boom, boom, 2 to the left. So go 1, 2. So right, it moves straight, 1, 2. Straight to the left 2. And so the final real graph is like that. It still has the same horizontal, still goes up to the right, but its center point is right there. And there we go. Which graph is that one? It's B, huh? B is the only one that's even close. Are we good? Are you liking these? No?
Not the worst.
Questions I can answer? All good? All right. Oh, by the way, you know what? You know the whole thing I told you about the horizontal? Now that we're talking about moving things, that's all that's really going on with the horizontal, huh? Meaning the normal horizontal, like the last one, he had no number out here, which means 0, which means the horizontal's at 0. So that's just, so what I could have told you is, look, the normal graph has horizontal at 0, and then if you have a number out here added, like +3 or whatever, that just grabs the whole graph and moves it up 3. Which is the same thing as me telling you whatever number's off to the right, that's where the horizontal is. Same thing, huh? It's just because you've moved the whole graph up, you know, whatever. So that's like in this one, the whole graph is moved, what? Down 2. Isn't it? That's all. That's another way to look at that same truth. Don't you? I like the way all the truths fit perfectly, right? In math, they do, because they're designed to do that on purpose, right? All these different truths agree with one another 100%. Different ways saying the same thing. Do y'all know what E is? Y equals E to the x minus 1. What is E? We're going to be getting into E now. From this point forward, we'll use it a lot. Do you know E is just a special number? E is just like pi is, right? Pi is 3.14 and goes on and on and on, right? E is a special number, 2.718, blah, 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 blah. It goes on and on and on. So it's just a special number. In calculus, you'll learn what exactly it is. It's the number, I mean, I'll say it, but I'm not sure how much it'll mean to you. It's the number who's his own derivative. It's the perfect number, E is, to be exactly his own derivative. So, anyway, you heard it here first. When you get to calculus, that's what you'll see. So anyway, E is a special number that does a really nice thing in calculus. So we really like it. So we use it in different things. But in the end, it's just a number. I want you to know, the main thing I want you to know is it's just a number. Like pi is a special number. What's so special about pi? What is pi? Like, why do we use pi? 3.14. Somebody just make that up one day and go, I just like 3.14. Anybody know what it is? Do you know, Mendo? You give me signals. Circle, yeah, something to do with a circle, huh?
The distance from the center to the outside and around it.
Yeah, you're hitting all around it. Yeah, basically, if you take any circle, they started discovering pi back in the, like, I think the oldest record is the ancient Egyptian days. They would find circles, anything in nature like a tree trunk or a stone or anything that was circular, close to circular, you know, and they would use whatever measuring tools they had, a little bit crude, but they would measure around the object and then straight across the object's middle, and they would divide those two numbers. Now, I don't know if you know, and they kept getting 3.14 or something close to it, depending on how accurate their tools were and how exactly circular the circular thing was. And that would work for little circles or big. And they found like a big old tree or a big old stone or a big old whatever round, and they measured all, whoops, can't do that. Measured all the way around the object, got some number, and then measured straight across the middle of the object. Divide those two numbers, you know, circumference divided by diameter, you know, all the way around it, divided by across it, and they just kept getting 3.14. No matter how big or small the circle was. They always got this same number when they divided around it and across it. They're like, huh, that's weird. Why does that number keep popping up? Well, now we know more precisely. Do you guys know the circumference of a circle formula? 2 pi r. That's how far around a circle. It's like pi r squared, but it's the 2 goes to the front. Area is pi r squared. Around is 2 pi r. What's diameter? What's all the... Radius is halfway across, right? So what's diameter? What's all the way across? two radiuses, huh? Right, because it's r each way. So diameter all the way across is 2r. So you see what happens when you divide those? What do you get? Pi. That's what's happening. That's what pi is. For any true circle exactly measured, the circumference of my diameter is exactly pi. So it's just something in nature. It's just true. It's just a property of a circle around. Anyway, so enough said. That's what pi is. It's just that ratio. E, so it's a special number. E is a special number. So in the end, when you look at this, I want you to think the following thought that will be helpful to you. This is not much different. You should think, hey, look, that's just basically 2.7 whatever to the x minus 1. I'm just going to do whatever I would do if they gave me a 2-something number. And that's right. There's no special rules here. You don't need to do anything amazing or fancy or special. So when you see that E, just think, hey, that's just 2-point-something. You don't need to put in, I don't mean you need to actually write 2.7. You don't need to write anything. But I just want you to think in your mind, oh, it's just 2-something. So it's just a special number, whatever. Okay, so I'm just going to do the problem as usual. It's just a special number. And so what am I going to do? Well, the thing I always do. So A times B to the x plus C. So what's my plus C? It's 0. That's the horizontal, is 0. What's my number multiplied in the front? I don't see anything, so it must be 1. That's my A. That's right. So let's do the graph. So the horizontal is at 0. So I'll put a horizontal asymptote at 0. Horizontal asymptote at 0. The A is 1, so go up 1 for the A. Like that. Put the dot. Now, this one goes up to the right, like any one that doesn't have negatives. There's no negative in the front. There's no negative on the x. But there is an x minus 1. So what's that going to do? To any graph. Right. Remember, x is opposite. Right 1. So it's just going to go right 1. There it is. So there's the actual graph. We're done. So which one is that? A and D both look kind of right, don't they? Is it A or is it D? I can't tell. Oh, it's got to be, it's A, isn't it? Because D has got to probably, I don't know if you can see it way in the back, probably not. But you can tell, when you do it on your homework, you'll be able to tell. It's already up at 2 right in the middle. Ours is below 1 in the middle. So it's not D, it's A. And there we go. Is that good? So E is just a special number. It's a 2-something special number like pi is a 3-something. Let's try that one. E is also the base for natural log, you might remember. We'll be heavy into that on Thursday. Try that one. Graph that thing. It might help if you put that's 7. Is that a positive 7 or a negative 7? Positive 7. It might help. You don't have to. But it might help to stick it back there, because that's how we're used to looking at it, huh? The added numbers off to it. If that helps. So that's the C, isn't it? That 7 is the C. It's where the horizontal asymptote is. Is that good? Then we got the 2 flips. We got a Y flip and an X flip, don't we? So I'm going to go, okay, horizontal, this is the horizontal. Asymptote is 7, 1, 2, 3, 4, 5, 6, 7. Up at 7. The A is 1, negative 1. So it's right here at 6. So kind of all cramming together here. So the A is down 1. This graph has been flipped. It's a Y flip and an X flip, both. It's been flipped both ways. So the normal graph goes up to the right. This one will go down to the right, but it's been flipped sideways. So it'll actually, do the final one here, it'll actually go like this, won't it? There's the actual one. Flipped vertically and sideways. Right? I rotated it about this axis, didn't I? So that last one, I grabbed this and turned it, and so it went like that. Right? I flipped it vertically, and I turned it sideways. Both flips. The A is negative 1. There it is. Which graph is that? It's D, huh? Clearly D. We good? We happy about all these exponentials? I think that's their sleeve here. Okay, so y equals 3 minus e to the minus x over 2. Yeah, I'd probably rewrite that to make it easier to look at. Put that 3 at the back and make that minus a half x. Might be easier for you to think about it that way. That's what it is, right? X over 2 is a half x. That's supposed to be a minus. I didn't make that very clear. Let me try that again. Good. Everybody see that then? So that 3 is the horizontal asymptote. So let's do that. Up 3, 1, 2, 3. Horizontal. And the negative 1 is the A in the front, so down 1. This one's been flipped vertically and horizontally. So at first it goes down, then they flip it sideways. So it's going to go, turn it sideways. I'm getting confused. Turn it sideways. Yeah, like this. That's right. Okay. Go like that. Let me turn it sideways and vertical. There it is. What's a negative half? Hardly anything. Remember a half multiplying x? When you multiply by half, it compresses it, but x does the opposite, so it'll actually stretch it wider. Anyway, who cares? Thing already goes wide forever. So generally look like that. Which one is that? Yeah, D. Good? Onward we go. Pictures, now the equations. We absolutely must finish this section today because I was hoping to start the next section. The next one's even bigger. Quite a bit bigger. Yeah, I got to move it. All right. How do we solve for x there? That's a great equation, isn't it? It's 7. I mean, you kidding me? That's solved by observation. Right? 10 to what power is 7? No, sorry, 10 to what power is 10 to the 7th? Well, 7, right? Solved by observation, they call that. I had when I was at Cal Poly getting my master's in math, I took this one class written by this my professor, Dr. Baser. She had taken this crazy smart genius boy guy from UC Santa Cruz, still named Whittam. I still remember his name. I never met him, but I read his insane book, and he was too. That says widow, huh? Widow. Whittam. Anyway, he was too smart to be a teacher or a book writer. He was just too smart to deal with humanity, I guess. Anyway, he had his PhD. Like Dr. Baser had taken him as professor at UC Santa Cruz. She said he had his PhD when he was like, I don't know, 23 or something. PhD, not bachelor's degree. PhD in math by 23, right? The doctorate, which, it's 4 years bachelor's, 4 years or 5 PhD if you're a normal human being. 9, 18 plus 9, 27 if you're just clean, right? 23. Anyways, this genius boy, he wrote this crazy book that Dr. Baser thought it was funny to have us try to read. And so us grad students, I remember reading, and I remember that he had this one, I still remember he had this one statement. He had in calculus you do something called integrals, and he had this integral of the integral of the integral of the limit of the limit. It was just like a awful mess of just complex stuff. And then he said, this was his explanation. This was this guy's effort to help me by clear observation. I still remember that. By clear observation. Then he wrote 3. All of that. It's 3. I'm like, how's all that 3? How in the world? And I spent hours. I spent many hours working things on the side and in the Cal Poly library and in the different rooms, working to explain why that was 3. I remember going by Dr. Baser's office, talking to her, saying, how is this 3? What, and she tried to explain it to me. I couldn't really understand it. I remember saying to her at one point, I said, nobody can read this book. Because I was talking to the other grad students, and none of us could understand this book. I said, nobody can read this book. I was kind of I was a little rude, really, to my professor. I was like, yeah, I liked her, but, I was a little ingrate. I was like, no, nobody can read this book. I was all firm with her. And she laughed. I know. She just thought it was funny. Anyway, so it became our joke that semester among the grad students by clear observation. If anything, we even added to it, to the most casual observer, by clear observation. So this one, I think, is by clear observation. I think that is true, by clear observation. And I think he wasn't really trying very hard to help the rest of us. All right, 2 to the minus x is 4. Can you solve that one? You could solve it by observation, maybe. Or you could do a technique. Can anybody just tell by observation? Yeah, what do you put x in there to make that true? What x value, what does x have to be? What number could you put in there that would make that true?
-2.
Correct. Tyler's got the observation going on. Do you see that? 2 to the negative 2 would be 2 to the positive 2 is 4. So if you can do that, great. If you can solve by clear observation, do it. So by clear observation, the answer is -2. Now, for those that are not as comfortable, and they're going to get way harder than this in a minute, so you need a method too. Let me give you the method. The method is make the bases the same. So if you can't tell just by looking at the thing, which nobody will in a minute, other than Whittam maybe, 4 is 2 squared, huh? 4 is 2 squared. So you see how I've made the two bases the same now? So that as soon as you've made the bases the same, you can set the powers equal. In other words, if 2 to some power is 2 to the 2, well then that power has to be 2, or 2 to one of them wouldn't equal 2 to the other. You with me logically? Does that make sense? If I say, hey, 2 to something is equaling 2 to something else, well those somethings must be equal. Or 2 to one of them wouldn't equal 2 to the other if they were different, right? So as soon as you've made the bases the same, you know the powers have to be equal, don't you? So you can just cut out the bases at that point. The powers have to be equal. And now finish solving this, divide by -1. There it is, the answer we had already observed, -2. Is that good? Make the bases the same. That's the method. I didn't realize they'd do that right away. Okay, so 4/3 to the x is 64/27. You know, maybe we should just do this on our calculator. Yeah, I would. Just take your calculator out for a minute, guys and gals, and just say, look, just do the top first off, and just say, hey, 4, just do the 4 for a minute. To what power is 64? So just take 4 times 4 times 4, start hitting the buttons. And you'll find, isn't it? Oh, just 3 of them, huh? Just 3 of them? 4 times 4 times 4 is 64, right? So that mean, and then, does that work for the 3 also? Is 3 times 3 times 3? Yeah. So that what's the power got to be? 3. Done. This has got to be 3. X is 3. Done. That's the easiest way. I'm not going to mess around with anything more fancy. Just take your calculator. Just check it out. 4, 4, 4, 3, 3, 3. It works. So, third power is what's needed on that. Good? Five to the 2x plus 1 is 25. Okay. So make the bases the same. So that one's probably too hard to solve by observation. Make the two bases the same. So step 1, make. So let me give you some method. Solving, yeah, let me write something for you. Solving x in power. Exponential notes. When x is in the power, so when you see one of these questions, I'm trying to help you categorize. That's a lot of the battle, huh, when you get to a math test. So next week on Thursday, when you get that math test in front of you, and you see x climbed into power,
X equals 1/2.
you think, oh, okay, yeah, Mr. Herring gave me some steps. When x is in power, step 1, make the bases the same. Step 2, then set powers equal and solve. So make the bases the same. Step 1, make the bases the same, and then eliminate those bases. And set the powers equal and solve. So 5 to the 2x plus 1 is 5 to the 2nd, right? Made the bases the same. That's step 1. Now, cut out those bases and just set the powers equal. They have to be equal, right? If 5 to something is equal to 5 to something, those powers have to be equal. Or 5 to one of them wouldn't equal 5 to the other if they were different. Then solve. 2x is 1 divided by 2, it's a half. Is that good?
I called it.
Make the bases the same, then set the powers equal. That's all you got to do for solving x in power. Well, for now. Good there. I flash off that. Okay.
On mine every time.
The ones you're getting are big, huh? Where is it? There it is. All right. So 4 to the x squared is 64. So what do you got to do? You got to take that 64 and make it out of a 4. You with me? So take 4 on your calculator and go, how many 4s do I need to multiply together? We just did it, huh? 3 of them equals 64. So this one becomes 4 to the 3rd with the x. Step 1. Base is the same. Am I going too quick? I'm feeling the push of time, but I don't want to race too far ahead of you. Is that good for the first step? See how I made the bases the same? I made that 64 into 4 to the third. Making the two bases the same. So that's step 1. Make the bases the same. So finish it from there. Now, cut those bases out. And just set the powers equal, right? And solve that. So cut the bases out. Step 2, powers equal. So x squared equals 3x. So we need to solve that now. Now, how do you solve x squared equals 3x? What do we do? You good with x squared, solving x squared? Any kind of x squared? Number 1, what do you always do? Get a 0. Remember, whenever you see x squared, you got to get a 0. Try to factor. If it won't factor, you can always do the quadratic formula. Right? Remember that kind of thing? So let's just jump this over. Get a 0. Is that good? So whenever we see x squared, whenever you see x squared, right away you get a 0. And then factor, that means take out an x. Right? Take out an x, take out GCF, take out the x, what's in common. And then you set each part that has an x with an x equal to 0. So the x alone is 0 and the x minus 3 equals 0. So that means x alone is 0 and x minus 3 is 0. Jump that over. X is 3. So the answers are 3 and 0. 2 answers. They want you to put them both in with a comma. Use commas, 0, comma 3. Either order. No parentheses. It's not a graphing thing. It's just 2 separate answers. 0, comma 3 or 3, comma 0 either way. Is that okay? Does that make sense? So base is the same. Powers equal. Whenever you have x squared, get a 0 factor. All right, let's move on. Okay, 64 to the 3x, 16 to the x plus 2. Try that one. So you got to make those bases the same.
Would we reduce both of them? Yeah.
Yeah, do you realize you can't make 64 out of 16? If you take your calculator and you take 16 times 16, it's already too big, huh? It's bigger than 64. So then you think, whoa, how do I do this? Make them both out of 4. Lower them both. Make them both out of 4. So this is going to be 4 to some power. This is going to be 4 to some power. Use your calculator. Find out how many. You can use the power button or the just 4 times 4 times 4. Just count them as you go. Step 1, base is the same. So 64, it's third power. Yeah, we did it a couple times. But there's also the other 3x that's out there, huh? And the other side is 4 squared. We good so far to there? So that makes sense. So I made the 64 4 to the third, the 16 4 squared. You could have actually made them out of 2 as well. So both 2 to some power. Anyway, good to hear so far? Now, do you know the rule about powers inside parentheses and outside parentheses? They times. So let me remind you. If you have 2 to the third, 2 to the fourth, those add. But if you have 2 to the third, 2 to the fourth, those multiply. So powers inside and outside parentheses multiply when they're on the same base. Remember that from algebra? But if you have 2 different 2's, each having their own base with 2 separate powers, those add. Right? Remember all that? Those different rules? So the main one to say is powers outside parentheses multiply powers inside. So that means these guys will multiply powers outside, multiply powers inside. 9x. And here this guy's going to multiply. 2x plus 4. Powers inside parentheses multiply powers outside parentheses. Now, cut them out. Set the powers equal. Right? Base is the same. Step 2, powers equal. So 9x will be 2x plus 4. Is that good? Is this making sense? Solve for x. Subtract 2x. 7x is 4. Divide by 7. 4 sevens. How we doing? We good? Gonna have to skip a few. Alright, so 9 to the x times 3 to the x squared is 81 to the second power. Alright, you got to make all those bases 3, huh? Make all those bases 3, and then you got to put those 2 together on the left side. Somehow, use the rules of powers. Nine to the x, 3 to the 2x, good so far? Now 81, 3 to the 4th, right? Calculator. 3 times 3 times 3 times 3. 9 times 9, 2 3s, 2 3s, 4 3s. Good to there? Now, you got to put these guys together because you got to have a single 3, a single 3. This one's 8. Put powers outside parentheses, multiply powers inside parentheses, right? But the other side, you got to somehow put these guys together. What is the 2x and the x? Are they going to multiply? No, because it's not. This is not powers outside parentheses and inside. There's no parentheses there. I mean, you might say, well, yeah, Mr. Couldn't we put? Yeah, sure. Even if you put them, so what? That's still nobody's outside parentheses, right? This is outside inside. This is multiply. So I hope I'm not confusing you by putting extra stuff in there. Just add them. It's just an add them up, huh? Like that. We good? Just there's 2 different bases. 2 bases multiplied, powers added. Okay. Good to there? Now cut the bases out, set the powers equal, right? Same bases. Set 2 powers equal. So cut out the bases. X squared plus 2x equals 8. Solve it from there. Remember how we solve x squared? X squared is different than regular x. X squared, you got, what's step 1? Gotta get a 0, yeah. Get a 0. So get a 0. Factor that thing. Get a 0, factor that thing. So jump that 8 over. What do we got? We've got x squared minus 2x minus 8 is 0. Right, that 8 comes over an 8. And then factor. What is it, 4 and 2? They have to multiply to be 8. Add to be negative. Remember, the sign in the middle always goes on the bigger. Remember that? Sign in the middle goes on the 4. Negative 4 plus 2 makes negative 2 in the middle. So there it is. And then, you said each one equal to 0. And it's just going to be opposite sign, huh? You can just skip this step if you want. So it's going to be what? Positive 4 and negative 2 are our 2 answers. There we go. Is that okay? Questions on that?
The 2x is positive, right?
Samuel, right? So the sign in the middle goes in the bigger.
Yeah, but that's positive.
On the right
That
is
was
what?
supposed to be positive. Didn't you subtract?
Oh, I messed up. You're totally right. Thank you. This is plus 2x. Thank you. I'm glad you said something. What were the rest of you guys thinking? Were you thinking I was just crazy, but you're being quiet about it? That was nice, but please speak up. Plus 4 minus 2. Thank you. So I totally reversed all these signs. Thank you. Yes, I'm just being goofy. So then x plus 4 is 0. X minus 2 is 0. John, I just copied the wrong sign over. So yeah, it's negative 4 plus 2, huh? Thank you. Good? All right. The end, I'm not going to get to with enough time to do a decent job on. So, but I'm also afraid to leave little things uncovered. So, time. All right. Chop. They've already got the same bases. Who cares that it's e? Whatever. It's just a special number. Chop them out. Bases are equal, so just powers equal. Solve it. Subtract 5x. So that's minus 4x is 24 divided by minus 4. X is minus 6. Good? Just chop the bases. Base is the same, cut them out. Doesn't matter what those bases are. Good. So I'll be fraction powers. What do fraction powers always mean? What do we do with fractions, guys and gals? What have we seen? Fractions mean negative powers. Write that as e to the negative 20. Right? That's always what they're hinting at. So, good to there? Negative powers? Good, good, good. Now, how do you put these guys together into 1e? What do we do? Powers add. Add, or, same thing, subtract. Add negative 20, so just minus 20, right? Same bases multiplied, powers add or subtract together. Good like that? Now cut the e's, right? Bases are the same, cut them out. Just set the powers equal and solve. So boom, x squared is 9x minus 20. Oh, how do we always solve x squared equations? Get a 0. So jump these guys over. Get x squared minus 9x plus 20 is 0. Bring it up here, x squared minus 9x plus 20 is 0. So 2 and 10, 4 and 5. 4 and 5, huh? 5 and 4, both negative, right? To add to be negative 9, to multiply to be plus 20, two negatives. So you know the drill. Positive 4, positive 5. There we go, we're done. Is that good? All is well. He's getting. So they're saying if 8 to the x is 7, what is 8 to the minus 2x equal to? That's our question. Kind of a weird question. How do you do that? Well, basically, we want to think of a way of turning this into the 8 to the minus 2x thing that they're asking for. How do you turn this into this?
Split the 8 and the negative 2.
Can't you just go negative 2 power?
Yeah.
Because power is outside, multiply power is inside, and that'll be that. But whatever you do to one side, you have no choice but to do the same thing to the other to keep them equal, right? If two things are equal, treat them the same, they'll be equal afterwards. Right? So you with me? So I'm raising both sides to the negative 2 powers so I can make the left side look like what they're asking me for. And then I just work out the right side. So what is 7 to the minus 2 power?
1 over 49.
Good. What does a negative power do? Flips it, right? 1 over 7 squared. In other words, 1/49. Yep. Good?
Everyone's all quiet.
Right. Let's try another one. 9 to the minus x is 14. They're asking, hey, what's 9 to the 2x equal? So think of what power you need to put on that left side to make that negative x power become a positive 2x power. And then do the same thing to both sides and find the answer. So what power do I got to put up here? What times minus x will be positive 2x? Negative 2, huh? Negative 2 times negative x will be positive 2x. Whatever you do to one side, no choice but do the same thing to the other, keep the balance. Negative 2, which is what? 1 over 14 squared, which is some big number, I don't know. What is that? 1 over 196, thank you. 196. They want a reduced fraction? That's what we gave them. Good? Everybody getting the hang of that? Just do whatever it takes to make the left side whatever they're asking for, and then do the same thing on the right. Negative powers flip. Multiple choice. They're just requiring us to just look at that picture and come up with the whole function. Here, let me just make that up the ante a little bit here near the end. So 27, all right. So basically they give you that and they say, hey, what's the function? So we know it's y equals a b to the x plus c. See what you can do. No multiple choice help, just straight. Let's take it piece by piece. What's that C look like? What's the C? C is always the horizontal. What's the horizontal? It's just 0, huh? Just flattening out of y equals 0, right? Good so far? So the C is 0. The horizontal, right? You can just tell it's coming down for a landing on the height 0 line, right? They're not showing the dotted line, but we can see it's flattening out at a height of 0, right? So the horizontal is 0. What's the A? Remember, A is the jump amount from the horizontal to the center dot. Well, there's the center dot. A must be 1. Good? Good to there so far? All got left to find is B? Is it really unclear what B is? It's got to be 6. You can see it all over that graph, but I'll get particular in it. It's b to the x, then I can plug in a point. Pick any point you want, like how about 1, 6? If x is 1, y is 6. 6 equals b to the 1. B is 6. Sure enough. So the answer is 6 to the x. That's the 6 to the x function. Because the c is just 0 and the a is just 1. The base is 6. Is that okay? On that? All right, real quick, I'll show this. All right, so they give me this to say, what's h in negative 2? So that means just plug in negative 2, doesn't it? So that just means 1/3 to the negative 2 minus 27, right? Just plug that in. You're doing good. And so what does that equal? What is 1/3 to the negative 2 power? Good, because it flips it, makes it 3 over 1, and then it does, and then the power becomes positive, right? Right, so negative, exactly right, it's going to be 9. Negative powers flip things, and then you do the power. The power becomes positive after it causes the flip. The negative part of the power causes the flip, and then becomes positive. So that's exactly right. So it's 3 over 1, or just 3 squared. 9 minus 27 is that minus 18? Yeah, minus 18. Is that good so far? So negative powers, the negative part of the power causes the flip. And then becomes positive. Good? And that's negative 18. What is the point on the graph? Well, the x was negative 2. The y came out negative 18. So that's the point, negative 2, negative 18. Does that make sense? Whenever you plug in and get an answer, that's an xy on the graph. Right? You with me? They're just making sure you're clear on that. Right? You guys with me on that? Whenever you plug into a function, we plugged in negative 2. That's our x value. And what answer you get, negative 18, that's your y. So x is negative 2, y is negative 18. It's a point on the graph. Part B. If h of x is 2/16, Now that means the left side. So they want me to make the left, here's part B down here. I want to make the left side 216. And they want me to, what is x, and then what is that point? So, okay, how do you solve that for x? That's more tricky. Solve that for x. What do you think? Add the 27. 232.43. Good so far? Now, how do you figure out that x power? We know what I would do, guys. I would 3 over 1. This, we're going to flip it. It's going to be some negative x power that's going to flip it, make it a regular 3 in just a second. I just need to know how many 3's to make 243. So I just take my calculator and go 3 times 3 times 3 times 3. Isn't it 5 of them? I think it's, yeah, 5 of them, right? Yeah, 243. Yeah, 5 of them. So 3 to the 5th, you know, your calculator will tell you that, is 243. So what does that mean the x needs to be? -5. Do you realize? Because the negative, put a -5 there, the negative will flip it, make it a 3, and then the 5 power will be 5 3's, 243. So x has got to be -5. Is that good? They're really pushing this negative power flip thing. Comfortable with that? So then what's the point? What is that point? Well, it's x -5, and the answer, oh no, sorry, the answer is the original h of x. Remember, this is your y. The function value is the y value. So it's the point is -5, 216. That's the y value and the x value. That's the point on the graph, right? Remember the x and the y, the h of x, that go together are a point on the graph. Good to there. And then part C, find the 0 of h. The 0. What's that mean?
It means the y is 0.
Y equal to 0. Yeah, like we're used to finding on a graphic calculator. The y equals 0, so maybe I'll go up here and do it. So that means set y equals 0. Whenever they say a 0, they mean y is 0. And so part C, a 0 means y is 0, or the function. Y values are function values. So you take the function h of x and you make it 0. And you solve for x. Is that good? You make the function value, the y value, 0. That's what a 0 is. Find the x that makes that happen. So solve for x. Add the -27 to the other side. You get positive 27 is 1/3 to the x. Good. So far, I just added 27 to both sides, really. Right? Get rid of it. Now, what x is here? What power do we need on the 1/3 to make it 27? Good? We all good with that answer? It's -3, right? Because the negative power will flip it to make it a regular 3 over 1, and 3 times 3 times 3, 3 times, it'll be 27. So there we go. You okay with those negative powers? Is that making sense? All right. Come talk to me or Roberto, or hit the buttons. So they give you this formula, 17,301, 0.92 to the x. And they say, how about if it's 3 years old? Well, x is the years old. So basically saying, just stick a 3 in and hit the buttons on your calculator. That's all they're saying. 17,301, 0.92 to the 3rd. Use your calculator. And then part B, put a 9 in. Hit the buttons again. Right? Because x is years old. And they're saying 3 years old. So x is 3. Hit the buttons on your calculator. That